Okay, so this video is going to start off topic 1 of mechanics of materials, which is stress and strain. I'm probably going to do this in a couple of videos just because we have 82 slides to cover, so the long amount to go through all at once. But basically, I want to introduce concepts of normal and shear stress and strain, and then solve a couple of problems that have to do with stress and strain as well. So the first thing I want to do is I want to go over a little bit of an introduction and a review of stress before we kind of jump into solving stress problems. Okay, so if we pull back from mechanics of materials, which is the class we're in right now, and we remember the prereq for this class, which is statics, right? Statics, and even if we remember dynamics, what we're doing primarily in statics and dynamics is we're studying the effect or external effects of forces on rigid bodies. So what's happening to a rigid body on the outside? So for example, you can think of yourself pushing a chair out and in from a table. What is the effect, the external effect of me pushing? My hand pushes the chair, it moves some displacement, that would be dynamics, or my hand pushes a chair from one end and someone else pushes a chair from the other end. Those forces balance out, that's more statics, right? When we get to mechanics of materials, we're now interested on what's happening inside, okay? What's happening inside of a system when forces are applied tells us a lot about deformations and how we can actually build these members and design these members based on how they're going to deform, okay? So it's kind of an overview of where we're going with this topic here, okay? So just a little bit of a review. I know stress is a word that we kind of use colloquially in a lot of different ways, like I'm stressed out, right? So the definition of that word that we actually use is not so different than the actual definition in engineering or mathematics, okay? There's just a little bit more, oops, it seems like there we go. There's a little bit more, again, like theory tied and connected to this. So what I want to talk about is, let's consider a person. Let's take this picture here. We have a person lying on a bed of nails, okay? I'm not saying this person that's sandwiched between the bed of nails isn't feeling anything, but they're definitely not being punctured by the nails, or they're not experiencing a level of pain which is intolerable necessarily, even though there is a person standing on top of them and there are little needles touching their body, right? So why is it that this reaction is different as opposed to having one nail there? If we were to think of this person as having only one nail on top and bottom and someone is going to be sitting on top, that nail most likely will puncture the person in the green or gray shirt's body and actually injure them. But what happens here, so I want you guys to think about this. What if there are 20 nails versus 200 versus 2,000? How many nails would you want there to be, more or less, if you were the person sandwiched inside? So I hope you're starting to think about this and that your answer is more, right? The reason for that is because what happens is the force is distributed per unit area here. So we have force, some force, this man, right? From statics, we know this force, he has some mass times gravity, mg, that's the force. But that force is being divided over a bunch of teeny tiny surface areas. So it's being divided by a unit area. And so the stress, this is basically stress. The stress isn't so bad. So you see, statics taught us a lot about forces, about this guy up here. Taught us a lot about forces. But as you can see, when it comes to actually the structural integrity of a member, we aren't necessarily concerned with how big the force is. We're concerned on how that force is distributed throughout the member, because that is going to tell us if the member is going, basically, is it going to make or break the member? Just like it's going to make or break this guy sitting in between the nails. Okay, that's the idea of kind of what we're going to be doing in all of mechanics of materials. It's going to focus on these different types of stresses. So before I move on to the next slide, okay, I want you guys to remember this is not a new concept. So stress is equal to force over area is, you probably have done this in mathematics, you've done it in physics before, so this is technically kind of a review. In this class, this type of stress, we're going to use this Greek symbol sigma to represent it, okay? And this sigma is, we have a lot of different kinds of stress. We don't have just one kind of stress. This sigma, this little notation here, this is normal stress. And the reason we call this normal stress is because it's perpendicular to the surface. So this is my surface, the stress acts perpendicular to that, and this is why we call that normal stress, like normal force, okay? The units of stress, okay, they're gonna be typically in, if we're talking about SI units or US customary, and I think I have another slide on this, I'm just giving you guys a preview here. Typically we'll use pascals, okay? And then here we could use something like pound per square inch or PSI. Okay, so we'll go over that a little bit more in the upcoming slides. So we already kind of discussed normal stress in this slide. We're now going to talk a little bit about shear stress, a different kind of stress. So what this little box represents here is, let's say I'm going to get rid of that picture for a second, and let's say I have a beam. Okay, let's say I have a beam that looks like this, and the beam is loaded with some force. This can be a simply supported system. I'm going to isolate one teeny tiny little section of that, and I'm going to show you guys what's happening on that system. So I'm isolating a teeny tiny little portion of that beam, and that's what this little box here, so that pink box on the beam, that's what this little box represents here. And every little portion, every little element on that beam is experiencing normal force in both directions. That's the sigma y going in the up and down direction, also a normal force in the sigma x. And if we remember from statics, when the sigmas or when the forces are pointing down, these would be in compression. They're imposing compression on the block, whereas these are pulling forces. So sigma x would be tension or tensile force. This would be in tension. But we also have shear forces, because remember, from statics again, when we expose internal forces, we have shear, moment, and normal force. We'll deal with moment a little bit later. We're going to focus on some more simplistic elements right now. So just shear and normal and how that translates to stress. So we also have tau, and tau here, this Greek letter tau, represents the shear stress, which acts parallel to each face of the element that we're looking at. Okay. So our causes of stress now, we have normal stress, sigma, we have shear stress, tau, and we have different items that can cause normal stress. So one item that we just talked about was axial. We also have bending. So what is axial? Just as a refresher, let's say I have a column and I have a force that is in line, the line of action of the force is parallel to the line of the member, something like this. This is axial force, right? Like a column. Okay, it can happen on a beam too, but typically it's a column, right? Bending, that's when we're talking about things like moment. Okay? Axial, this is where we're talking about normal force. This is that tension or compression. Okay. Now shear stress, which is parallel to the face, right? Remember the little block that I drew? We can discuss average shear stress, transverse shear stress, and shear stress from torsion. And we're going to go through all of these in more detail, okay? I'll give you an idea. Let me see if I go over all. I think I do. I'll give you an idea of each of these in the next few slides. So we're going to break down all of these: axial, bending, average, transverse, torsion in the next few slides. And this is also a really good preview of what this whole class is kind of going to look like. So we're going to cover almost everything that this class covers, but then we're going to take each one of these items here, and these are almost one topic per item for this class, okay? So the first cause of stress, we have axial. Right, so I drew this in the form of a column. Right here, now it's drawn in the form of a beam, where we have a beam being pulled from both sides by a force F. So of course, our sigma is going to be force divided by area. And it doesn't matter at what point we're looking at along the cross-section of the element, we have the same force divided by area, the same force divided by cross-sectional area, regardless of where we're looking at that on the member. Okay, it's constant along the entire cross-section of the element. Okay, the next type of normal stress that we can have is due to bending. So I want you guys to think about this for a second. So if I have my beam, right, and let's say I have some simple supports, And typically my beam is loaded perpendicular to my cross section like this, some force. Okay. When this beam, actually I should draw this, let me draw this as a full square or rectangle so you guys can see when I talk about tension and compression. Okay. And again, it's loaded, some force. Okay, so now what's happening is if this load is pushing down, we're gonna have some deformation, some small deformation of the member. This would be that top one right here. This is the top bar. And I'd have something with the bottom bar, right? And this would basically be, I draw it in, an exaggerated form of what that would look like when it's loaded with the force P. So if you guys were to look at this, do you see how when I'm loading this, I'm experiencing some rotation, I'm bending, and the top fibers of the bend are in compression, but the bottom fibers of the beam here are in tension, right? So I have compression and tension, okay? That's what I mean here by bending, top in compression, bottom in tension. So here, what we have is the center of the system basically experiences no stress, okay? And again, as we get through the topics here, I'm gonna derive that for you so you guys can see what I mean when I say that the center line of the system here has zero stress, okay? And this center line here has zero stress, okay? That length doesn't change. That's called my neutral axis. So we'll get into that a little bit more. But basically the formula for normal stress due to bending is moment times this value C, which corresponds to my neutral axis, divided by my moment of inertia. So we don't have to worry too much about these equations just yet. We're gonna get into them in a lot more detail in the next few topics, okay? Again, this is just a preview. So now continuing causes of stress, we've talked about axial, we've talked about bending. We're gonna move on to average stress now, average shear stress. So here, what I have, imagine I have, I'll show you an application of this. Let's say I have, and then I'll talk about the single shear and double shear. Let's say I have a beam and I have a force on the beam of 20 kilonewtons, and I have another force here, let's say of 20 kilonewtons. And let's say I make a cut along this beam, okay, right at the 20 kilonewton load, okay. What's going to happen is right here, I'll have a shear of 20 kilonewton, okay? And this gets distributed over whatever surface area I have here, okay? Gets distributed over whatever surface area I have here. And of course, this is really a 3D area. This is really a 3D area. It's going to, can't really, something like this, right? So this is a 3D area. And I can say that my tau average along the whole cross section is equal to the force divided by the area. Okay. Now that's for single shear. So what I have here is a bolt system, and you can see here only one plane passes through. So I only need to divide the shear force by A, but here if I have two planes, I need to divide the shear force by 2 times that area. Okay. And my last type, or actually no, second to last, I also have torsion. Second to last type of shear stress is transverse shear. So for this type of shear here, we're going to use the formula VQ over IT. And again, we're going to derive that later. But what we see here is that this is not uniform along the cross section. And again, with that derivation, we'll show why. And the last type of stress that we have to deal with is torsion. So remember, torsion is like moment, except now you're twisting about the x-axis instead of rotating about the z-axis. So we have our own special formula for torsion, which is TC over J. J is my polar moment of inertia. Okay, so these are all of the formulas that we'll be deriving throughout topics 1 through 10 of this class, okay? So this is what you can expect to see. By the end of the class, you should know how to solve for normal and shear stress due to axial, bending, average, transverse, and torsion. Okay, that's kind of the goal here. And here's a little summary slide for you to kind of work with throughout the course, or even for any of the topics we're gonna go over, okay? All right, so before we move on, we're gonna go over a little statics review. So I'm gonna say this here, you probably have heard me say it in class if you already had class before, and if you took statics with me, you've probably heard me say this in statics, but the information you learned in statics is super important for your success in mechanics of materials, in structures, and in your successive classes. So now is the perfect time, if you have any deficiencies in statics, to go ahead and address them. Some of the most important areas that you need to review are internal forces and shear and moment diagrams, okay? Don't worry about the rest of statics right now. Focus on those two areas. I'll write that for you. So internal forces and shear and moment diagrams. I do have a review up on Canvas titled Shear and Moment Review. It's a very detailed review, so I suggest that you go ahead and make sure you can solve all those problems, okay? Because this class has to pick up where that class left off. If you can't do the statics, you can't do the mechanics of materials, okay? So this is probably one of the only times I'm going to be reviewing statics. After that, I'm probably going to go through the statics a little bit quicker so that we can focus more on materials, okay? So types of external loads that we have surface forces and we have body forces. So when we're talking about statics and we're talking about civil engineering, most of the time the forces that we're dealing with lie right here in this category. Dynamics is going to deal with this a lot here. We're not going to deal with it so much, okay? We have different types of support reactions. Make sure you're familiar with these, and the super important ones are external pins, internal pins. Here, external pins, internal pins, fixed supports, rollers, but we also will deal with smooth supports and cables sometimes too. Okay, so all of these are super important. Make sure you understand the concept of what a support is and what it does. For example, a fixed support means you cannot move in any direction and you cannot rotate, whereas a pin means you can't move in any direction, but you can rotate. So make sure that that makes sense. And of course, we have equilibrium, which is kind of the core of statics, which is summation of forces has to be 0, moment has to be 0, whether you're talking about 2D systems or 3D systems. So here we have a 3D system and a 2D system. We're going to try primarily to stay in this range. However, we may do a couple of 3D problems here and there, but most of the time, this is where we're staying with 2D. Okay. Internal resultant loading. So this kind of potato shape is what they show in the book a lot when they're showing bodies, but I think it's easier also if I show you guys a beam as well. So imagine I have a beam here. Okay. And imagine I have some pin, some roller, something like this, and I make a cut along the beam anywhere. What happens here is I expose some internal forces, right? I'm going to draw them in red. So the first force I expose some normal force. I also expose some shear force, and I also expose some moment, right? I have another force here that I've put as torsion, okay? Torsion, I'm not going to show on this diagram because torsion is best shown on 3D systems. This here is a 2D system, but basically, if you take your right hand and you curl your fingers, you think about twisting. That's what torsion is. Or if you take your arm and you kind of twist your forearm in one direction, you kind of feel that burn on your forearm, right? That's because you're twisting your arm and it's basically undergoing some torsion. You're applying torque and it's undergoing torsion. Okay. Now this is for a coplanar system, so this is basically what I just drew up here. Coplanar means 2D. So this is just showing you that it could be any shape. However, I'm going to try to resort more to structural members, which is why I'm showing this to you in the form of a beam, really. Okay? So let's go ahead and solve example 1 here. Determine the resultant internal loadings acting on the cross-section at C of the cantilevered beam shown. So cantilever beam means it's fixed at one end, which is A here, and it's free at the other end at B. Okay? So what I want to do, the first thing I want to do here, it's pretty straightforward. I just want the internal forces at C. So the first thing I want to do is make a cut. And I'm going to make that cut exactly where the problem is asking, which is point C. Okay, now as I do that, I see that if I approach this from this direction, I'm actually going to show you the cut from the other direction as well. Okay, I have two cuts here. I just basically cut the member in half. So really I have exposed, I'm going to draw both of these. So I've exposed normal force at C. I've exposed a shear force at C. And I've exposed moment at C. And as we know, these are all equal but opposite direction. Okay, so I can pick. I can either solve this part of the cut, or I can solve this part of the cut. Part 1, or I'll call this A and B. Okay, I'm going to choose B because if I choose B, I don't have to solve for what's happening at A. Okay, so I'm going to go with this guy right here. Okay, so here I know that the distributed load is 270 for the entire 9 meters. But I want to know, well, what is the value of the distributed load here at 6 meters? So if I know that the whole load is 270 for 9 meters, I want to know what is W for 6 meters. That's how I can find that. And I can say that W is 180, and that's the magnitude of the distributed load. I also know that the resultant acts 1/3 away, right? It's just a centroid, the geometric centroid of this, which would be 2 meters. The rest of this would be 4 meters. And this value here is the area of a triangle, 1/2 times 180 times 6, 7, 8, 9. And I get 540 newtons. And you guys, remember, this is my free body diagram. I will always ask you for this. 90% of the problems, I will always ask you for a free body. Okay. My next step here are equations of equilibrium. So the sum of my forces in the x direction equals 0. I basically just have negative normal force at C equals 0. So I get 0. Summation of forces in the y. Up is positive. I get VC minus 540 equals 0. And I get VC is 540 newtons. And I'm going to sum moments about point C. Counterclockwise is positive. I get negative moment at C minus 540 times 2 is 0. And I end up getting MC is negative 1080 Newton meters, which basically means the negative means MC acts opposite of what I'm showing on the free body. So really MC is 1080 Newton meter. I'm showing it clockwise. It's really counterclockwise. So these are my answers right there. Okay, let's try another statics example here. I want to determine the resultant internal loading acting on the cross-section at G of the beam, and each joint is pin connected. Okay, so first thing I want to do, again, I'm going to draw the FBD of this whole structure. Okay, I'm trying to decide if I want to redraw the structure or draw it directly on it. Let's see, let's just, let's try drawing it on this and see how it works, okay? So I already have some forces on there. I'll go ahead and write or draw the resultant of this here. So again, the area of the triangle, 1/2 times 300 times 6 is 900. And here I have a pin, I have EX. Here I have EY. And here I'm actually going to draw this as my force, my resultant force FBC of the member, of that member, that two-force member, right? So this is the member force, not the reactions in the hinge, because I don't really need the reactions in the hinge. Okay. Okay. So the first thing I can do here, the first step I can do, well, my FBD is step 1. Next, what I can do is I can sum moments about point E. I can say counterclockwise is positive. I get negative FBC times 3 plus 1,500 times 10 plus 900, the resultant of the triangular distributed load, times 4. Set that equal to 0. Okay, my only unknown here is FBC equals 6,200. Okay. So now that that's done, I can go ahead, number 3, let's sum forces in the y direction. Let's see what we can get with this. I get negative 1,500 minus 900 plus EY is 0, and I end up getting EY is 2,400 pounds. Okay. All right. Next step. So we want to get FAB here, right? Which is this guy. We want to figure out what this force is. Okay, before we can solve for what's going on at G. Okay, so here to get FAB, the first thing we can do is isolate that joint at B. Here, you can see this is like a little truss system. So let's isolate this joint and apply method of joints here. So if this is point B, okay, I have FBC already solved for as 6,200 pounds. I don't know what FBD is, and I don't know what FBA is, right? I know this is a 3, 4, 5 triangle, so let me go ahead and okay. And what I can do now, I'm going to draw my X and Y axes here. And I'm going to start summing in both directions. So I can say the sum of forces in the X direction need to be 0. This direction is positive, and I get 6,200 minus FBA, which is a component in the 4/5 direction here. And I can get FBA equals 7,750 pounds. And I can sum forces in the Y, up is positive, and I get negative FBD minus FBA times the 3/5 component equals 0. And here I'm going to plug in the 7,750, and I can get FBD is negative 4,650, which means it actually acts in the opposite direction. So really it's going up. So it's 4,650 pounds going up. Okay, now I can finally set up my cut here. Actually, this is step 5. I can finally set up my cut. So this is point A, and this is point G where my cut is happening. I have a 1,500 pound load from the problem. I have FAB, I'm drawing a different color here. Okay, and I also, now that I've made a cut, have exposed some internal forces, of course. So I have normal force. I have a shear force. And I have some moment at G. And this is actually what I'm trying to find. So I just had to go through and solve everything else using statics to find those internal forces. So now I can sum forces in the x direction. Again, right, this is just the same process over and over. And I can get my normal force at G is negative 6,200, which basically means I have 6,200 pounds in this direction. I can sum forces in the y direction. And I get negative 1,500 plus 7750 times 3/5 component minus the shear at G. And I get shear at G is 3150. And lastly, I can sum moments about point G, counterclockwise is positive, and I can get mg minus 7750, the 3/5 component, times the moment arm of 2, plus 1500 times the moment arm of 2, and I get mg is 6,300 pound-feet. Okay. So a lot of statics work to get just 3 internal forces of the member, okay? All right, I have another example here. Let's see if that's the last one, and then we're gonna go talk about stress and strain. So let's solve this example, then we will probably, I'll probably stop this video here, and that'll be part 1 of this video. So let's go ahead and do this example. We want to determine the resultant internal loadings acting on the cross-section at B of the pipe, and A is subjected to a vertical force of 50, a horizontal force of 30, and a couple moment of 70, and so we're going to neglect the pipe's mass, just like the problem tells us. So actually, we're going to do a scalar analysis here. We don't need to use a Cartesian vector system here because the forces are pretty simple and they're acting directly in the x, y, and z direction. So there's no point in having to do Cartesian coordinates for this, or sorry, Cartesian vector analysis for this. So we're going to use our 6 scalar equations of equilibrium. So we're going to use summation of fx equals 0, summation of fy equals 0, summation of fz equals 0, and then of course our m in the x direction, our m in the y, and our m in the z. Okay. So let me actually come here. What I'm going to do is I'm going to redraw this to show you guys what we're even solving for. So this is my x, this is my y, and this is my z. So this is the right-hand coordinate system where your thumb represents the positive z-axis and your fingers curl from the positive x to the positive y. And what we're actually looking for here, so this pipe kind of comes out on the y-axis. I'm going to draw a little more straight and goes something like this with a little curve though, right? Something like that. Okay. And what we want to know is at some point B, we want to make a cut. So we're going to kind of try to draw this. We'll make a cut at B. And what happens is here, I have we'll start with the x. I have my FBX, right? These are the internal forces that I'm exposing when I make this cut. I'm sorry, FBZ. And I have my FBY. And then I'm going to use a different color here for my moments. So I have all of these internal forces, and that's basically what I'm trying to solve for here, given the loading on the system. So if I come here and I sum my forces in the x direction and set them equal to 0, Okay, I can see directly that my FBX is 0. I have nothing acting in the x direction, right? I have nothing acting in the x direction. Okay, I'm looking at this right here, the applied load. See, I have 50 in the z, I have 30 in the y, and then I have a couple moment, but I don't have any forces acting in the x direction, so my FBX has to be 0. Okay, for sum of y equals 0, I have my FBY, and now I have a 30 Newton force, so I know that FBY has to be negative 30. And then I can do the same thing for, I'll just do it down here, sum of forces in the z, FBZ minus that 50 Newton force, and I get FBZ is 50 newtons. Okay, now for my moment sums. Okay, and then I'm going to do, I have 2 more equations to use, and I have 2 more unknowns, so it's going to work perfectly. I have 30 times 1.25 equals 0, and I get MBZ equals negative 37.5 Newton meters. Okay, now I can get my resultants. So here, I can get my resultant normal force as, which is just my 30 newtons. Y is the normal direction here. My shear is going to be the VB, which is going to be the square root of my 0 squared and my 50 squared, which is the x and the z. This is y, this is x and z. I can get my torsional moment. That has to be my MBY here. Because my twist here, the system twists along the Y. And lastly, my bending moment. I have MB equals square root of 45 squared plus 37.5 squared. This is my X and my Z, and I get 58.6 Newton meters. Okay, remember from statics, let me put all these here. Remember from statics, our bending moment acts about the axes of the members that are perpendicular, and our torsional moment acts about the longitudinal axis of the member. This is how we got this. So bending moment torsional moment Okay, so we're going to stop here for this video and continue in part 2 in the next video.